Hello. Sorry. Um, Sorry for a few minutes delay. Um, yeah, I haven't checked out this wireless speaker. Seems not working. We have to go back to this little bit annoying speaker. Um, yeah, some of you told me this is kind of like too loud. I try to keep the distance. It's too loud. I agree, but this one doesn't work. But if you want me to adjust the volume, just let me know. Okay. Okay, so regarding the course policy, we would like to emphasize a little bit. First, uh, we have updated the office hour. So you could see that the time is scheduled here. And the good thing is that we always have this single office, which is in a map. It's mechanical, not mechanical, it's a computer science building, along with chemical engineering, a big building in this room. And we have the uh, 1 hour office hour for every weekday, and plus my own office hours. Like feel free to seek for help. And also we have a one TA whose case a little bit special. He has some like family obligations, has to do the remote office hours, and he has some like scheduled Zoom link. But we won't post the detailed link in the public official, the public website. We just put it in Canvas syllabus section. You will find it. Okay. That's one thing. And another thing is that we actually have released our very first quiz on Canvas. I hope you have noticed that. If it's not, please just take a look. The due will be tomorrow, 11:59 p.m. I guess. So there's just the three single choice problem. So it will take less than 5 minutes, but just please keep doing that. Don't forget to do that because we'll have like quite many quizzes throughout the semester. We won't have like room for makeups. So just make sure when it is released, you allocate some 5 minutes to finish that. And if you happen to miss a few of them, that's fine because eventually we'll just drop two quizzes results with lowest grade. Like just make sure like don't miss too many. Okay, and the third thing about the regrading request, because this is a pretty important and throughout my experience, because everyone cares about the grade, right? So if you want to request some regrading or you want to argue about some points, you want to argue for points in deduction or increase, please submit a Canvas command in the grade section. So I guess everyone is familiar with Canvas. If you look at the grading book, you'll see your grade and some comments left by the TA. And if you feel upset or if you don't agree with their decisions, just submit the comment there. The TA will watch that, but just make sure you should submit the request within 1 week after the grade is released. Right? You can't say like, okay, at end of semester, you came to us and say, okay, I request to grade my homework 1. That's a little bit too far. Okay. Okay, that's pretty much the things we want to emphasize regarding the course policy and the syllabus, and all those are documented. So if you're unclear and you want to look at again, just click this link. Okay, any question so far? Okay, so now we're going to start talking about very first concepts regarding our course, right? So I have to switch to iPad. Is it clear for everyone? Okay, thank you. So today we're going to start introducing some very fundamental concepts. So as we discussed in our last lecture, right? This course is talking about how do we more formally and rigorously talking about uncertain things or random things, right? And from which terms should we start with, right? We're going to introduce what does it mean by samples, sample spaces, events, and the probability on those events. Right? Those are all some basic concepts. So those concepts are defined based on very preliminary and fundamental term, which we believe everyone is familiar with. It's called set. Right? So what's a set? Anyone give me a definition? I mean, other than this. Or some intuition. Yes, exactly. Very, very good, right? It's just as defined literally, right? It's just a group of items, but just to make sure that those items are not identical to each other. So this is called set, right? So a set is a collection of unique objects, right? Unique just means like non-repeatable, non-identical, and here objects are not just abstract numbers, symbols. They can be anything. They can be anything you feel like can be called objects. Like they can be apples, it can be oranges, it can be human beings, it can be cats, whatever, right? So of course, you can also use set to describe abstract things, right? Numbers, colors, and so on. So here we give a few examples, right? So here we have a set of 3 numbers, right? 3, 8, and 31. And here we have a set of, I should call it fruits, right? So apple, pear, orange, and grape, as we just mentioned, right? You can put anything you want into a set. Right? However, just to make sure that a valid set should not contain duplicated elements, right? So if we put a set like this, it's not a valid set. Why? Yeah, we have 2. This number appears for twice, right? That's not a law. Set should be just a list of unique items. Okay. And another thing about set is that we don't care too much about the order. So in whichever order you put items in your set, it won't change the nature. In other words, we will them as the same set, right? Say you can represent this side as 3, 1, 2, right? Or 1, 3, 2. They are all exactly the same set. Right? Set has nothing to do with order. Okay. And once we define the concept set, right? So we can verify if a particular object is inside the set, right? And if that object is in the set, we call it belongs to the set. So we use this symbol, right? Just Greek letter, right? So abstractly, right, for any object X, if it is an element of a set A, then we denote X belongs to A. Right? And how do we denote X does not belong to A, or X is not an element of A? Yeah, I believe everyone knows that, right? It's just X not A. You put backslash in front of this belong to symbol. Okay, if X is not in the set A, we denote this as this guy. It's just a symbol. And among all possible sets, there is one special set, right? Which is a little bit, well, unrealistic in word, but it's very important in fundamental theory, which we call empty set or null set. So empty set or null set just means that this is a set with nothing in it. Okay. So it's like a very inaccurate analogy is like a zero. Like it's like zero, like origin from starting, right? So set the zero, the empty set has the same thing. Because in the future, if you want to study more in depth about the probability theory and the corresponding say sigma algebra or sigma field, this kind of stuff, the empty set plays a very, very important role. Okay. Let's walk through some important sets, right? And it could be, it's a little bit abstractive. It's not that realistic, but it is very useful, especially in math. Say, we denote all integers as the set Z, right? So how many elements are in this set? Any thought? Yes, exactly, right? So remember, sets could be finite, could be infinite, and even in extreme could be infinite, uncountable, right? So once things becomes like infinite, uncountable, you will have a lot of like unintuitive results, right? But it's not the focus of our class, but just give you a sense, right? Natural numbers, right? We know natural numbers are just non-negative integers, right? Starting from 0, 1, 2, 3, 4. So use this n to represent the natural numbers, which is essentially another set. Real numbers, right? Everybody knows real numbers, right? Real numbers is essentially a set, right? It contains all possible real numbers, right? Can be written down in decimal form, right? So real number or real numbers, this is a infinite uncountable set. Why it is uncountable? Yeah, that's a real number. That's about real numbers, right? So I'm talking about why this real number set is not only infinite, but uncountable. Yeah, that's intuitive, right? Oh, yeah. Yeah, yeah. That's a correct answer, but anyone can give like even more, I think, straightforward answer for this. Yes, exactly. This is a definition of countable or uncountable. But I mean, all your answers are correct. I just want to give you the most straightforward answer. So countable means that you can index the items in a set with natural numbers. 0, 1, 2, 3, 4, 5, 6. Right? Means that, okay, suppose I write a set, right? A1, A2, A3, right? So you see that we have 3 items in this set. And I have indexed these 3 items, 1, 2, 3, right? In other words, we can iterate this item, so one by one, right? But for real numbers as a whole set, you will never be able to find a way to iterate each element or enumerate each element. That's a very well-known result in real analysis and calculus. I'll just give you a sense. So here are some examples of real numbers: 5, 17.42 pi. Right? And remember, pi is an irrational number. What is irrational number? Yes, right. So irrational numbers means that you have an infinite number of digits and you don't have repeated patterns on that. Like if you have repeated patterns, it's still rational numbers. Okay, so we gave some like examples of sets, right? And we'll find once we have these definitions, we want to talk about the relationships between different sets, right? Like when we talk about numbers, we want to know if A is bigger than B, C is bigger than D, or the operations among those numbers. Right? Similarly, we want to say for how are we going to describe sides according to their relationships. So the first kind of relationship is to describe sets and subsets. So we know natural numbers are all non-negative integers, right? And Z is all the integers. And of course, the natural numbers are a subset of all the integers, right? So in other words, we can define natural numbers as picking up a particular set of numbers from the integers, right? We can represent the natural numbers in this way. So basically, we say it is a collection of all the members in Z such that this member X is non-negative. Right? This is how we describe or define natural numbers using the so-called conditions. Right? So conditionals, just as a way to extract a subset out of some like bigger set. Right? We can also define the so-called even integers, right? We know that is all, of course, is also a subset of integers, right? So we can define this like this one, right? So it's all the elements in Z who is divisible by 2, right? And how can we define set of all numbers? Yes, exactly, right? You just change the conditional, right? So you can just put it not here, right? And that's it. Rationals, right? And rationals is a set defined this way, right? So we know all the rationals can be written as some integer divided by another integer, right? So that's how you can write the definition of rationals in this way. So we're gonna have an element who's satisfy this form, P over Q, and both P, Q are elements in integers, and Q is not zero. Does it make sense? Okay. Okay, now we want to give a more formal definition of subset, right? We call a set A is a subset of another set B if for every element of A is also an element in B. Right? So if we write it formally, it will be like for every X that belongs to A, X also belongs to B. Right? Then we denote it as A um, is a subset of B, right? We use this symbol. Okay, now let's see some example, right? So this is our A, this is our B, right? We can just check, right? So every element in A, we have two elements in A, 1 and 9, right? 1 belongs to B, right? 3 belongs to B. So that verifies every element of A is an element of B. So A is a subset of B. Any questions so far? Okay. And this is the basic fact, right? The rational numbers, Q, is a subset of real numbers, right? Like real numbers are just rational numbers and the irrational numbers, right? So, and now let us look at this set. Right? This is our A, this is our B. Right? So unfortunately, there is some kind of overlap between A and B, but A is not a subset of B. Why? Why A is not? Yeah, exactly, right? So we only see that apple is in A and also in B, but pear is in A, yet is not in B. So we cannot say A is a subset of B. Okay. So this is a very important definition, right? So the point is that you must make sure every element in A must also be B in B. Then you could say A is a subset of B. Otherwise, sorry, you cannot say anything. And one other thing about subset is that the empty set by default is a subset of any set. This is a little bit weird, right? Empty set is actually contains nothing. So there are actually no element in an empty set, but we still require that the empty set is a subset of any set, right? This is like some kind of an axiom, right? We use it by default. Any questions so far? Okay. Another thing is that for any set, it is a subset of itself. Why? According to the definition, right? Every element in A is obviously in A. So A is a subset of A itself. Okay, there's a little bit like additional definition to the subsets. It's called a strict subset, which we use this symbol. So we don't have an extra bar here. Okay. So if we remove the bottom bar, right, we just write this one, it means not only every element in A, which is also in B, but also there is some element in B, but does not belong to A. Just like B is, roughly speaking, it's like B is bigger, strictly bigger than A. Okay. For example, I can say 1, 2 is A, right? And B is 1, 2, 3. Then we know that A is a subset of B, right? But there is some element 3 here, which does not belong to A. That means like B is strictly bigger than A. So we'll see A is a strict subset of B. Oh, sorry, here, strict subset of B. We don't have that part. Okay. That's why when we talk about for any set A, like, okay, it is a subset of A, but we cannot say A is a strict subset of A, right? Because there's no element in yourself which is not inside yourself. Okay, any questions so far? Okay, great. Next, we talk about the concept called sample space. Right? So sample space is the set of all possible outcomes of an experiment. So you see why we introduce the concept set beforehand, right? Because sample space is a special set, right? This set contains all possible results for one experiment, right? And because we're going to talk about probability, right? Random things, right? So that means this experiment is really random, contains some like randomness inside. So, and we want to study the chance of every possible outcome. So we first define this concept called sample space, which includes all possible results from your experiment. Right? We usually denote the sample space as this big omega. So now, examples, right? To be more concrete, suppose your experiment is to flip a coin, right? Toss a coin. What are the possible outcomes do we have? Right? Well, we actually have two possible outcomes: heads up or tail up, right? That's why our sample space will be written in this way, right? We have two outcomes, two possible outcomes, heads and tail. The second example, right? Suppose you roll a die, right? And how many outcomes do we possibly have? 6, right? If you look at dice, right, there are 6 faces, and each face has one number, right? So that means like we could possibly have 1 point, 2 points, 3 points, 4, 5, 6 points, right? So our sample space will be like this. Right? And suppose you're doing some kind of like random picking up game, right? You're in front of a bucket of red and black balls, right? And what are the possible outcomes for your one pickup? You could possibly pick up a red ball, you could possibly pick up a black ball, so our sample space will contain this both outcomes, right? So red and black. Okay, any questions so far? Everyone's comfortable with this definition, right? Okay. Okay, so now let us think about it a little bit more in depth, right? So suppose now our experiment becomes tossing a coin for twice. Then what is possible? What is the sample space? . . 。 . 。 . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . 。 . 。 。 . 。 . 。 . 。 . Yes, exactly, right? Again, we just follow definition, right? So you sample the corn, you flip the, you toss the corn for twice, right? Then you should look at all possible outcomes you have, right? The first one could be, okay, the twice, you both have heads up, right? So it'll be heads, right? Or the first one is head and second one is tail, right? Third one could be first, the third outcome could be the first one is tail and the next one you see heads up, right? The last one is that, okay, for both, you see, for both tossing, you see tails up. So then this is our sample space. And this one is a little bit even more brutal, right? Shuffling a deck of 52 cards. Can anyone briefly describe what are the sample space? What is the sample space? Exactly, right? So you just consider like you shuffle a deck, right? So you got 50 cards, and actually the matters is just how the order of those cards, right? So of course there are many, many possible orders, and there's a big sample space. Right? Okay, so now we define the sample space, which represents all possible outcomes for doing one random experiment, right? And based upon sample space, then we define the definition of event. We define event. What is event? Event is just a subset of a sample space. Remember, sample space is a set, right? So you have many possible subsets. And an event is just a subset of a sample space. So how does it relate to the event from our natural understanding? Let's pay attention. So you want to describe some kind of event like this. Right? You roll a die and you got an even number. I mean, this is a kind of very natural description of the event or the result of your experiment. Of course, your experiment now is roll a die, right? But mathematically, we are gonna express this event as a set which contains all the even points you might have after rolling die, right? So which is just 2, 4, 6. And the sample space, as we defined, is the universal set of all possible outcomes, right? Of course, this 2, 4, 6 is just a subset of the sample space. Does it make sense? No, no. Right? Again, we're defined, we're based upon the definition of set. Okay. Another question? Okay. So another event is that you flip a coin. This is your random experiment, and you see head up, right? So this is how naturally, verbally, we're going to describe the event, right? Mathematically, we're going to represent this event as a subset which contains one element, H. Right? And of course, our sample space is H and T, right? And again, it is a subset of the sample space. And this one is another example, which is talking about, okay, suppose you're a software developer, right? you write a piece of programming code, right? And we're going to describe this event. Your code takes longer 5 seconds to run. Right? So this is how we say that, right? You run faster than 5 kilometers per hour, something like that, right? And mathematically, this event actually is represented by an interval, right? It's 5 to infinity. This actually represents all the real numbers bigger than 5, right? This is the definition of this interval, right? And our sample space is actually all the real numbers, right? And actually, to be more accurate, this will be all the positive real numbers, right? Because your code won't run for negative 5 seconds. Right? So that means this event, which mathematically is represented by this interval, is a subset of our sample space. Any questions? Okay, great. Okay, so next we're going to talk about the operations between set, right? So you see that set and set, they might have some like reaction between each other and to generate new sets, right? And in mathematically, this is how we operate between events to generate new events. Okay, the first most important operation for sets is called union. The union of two sets, A and B, which is denoted this way, is the set of all elements in either A or B. So basically just to combine all the elements in A and B together and deduplicate. Let's see the example. So A could be 1, 3, 5, right? B could be 1, 2, 3, right? And these are just represents two events. The first event is you roll a die and you get some odd number, right? The second event is you roll a die and your point is less than or equal to 3. Okay. So when we do the union, you see that we just combine the elements in both sets, put them together, and remove the duplicated ones. Now, I mean, deduplicate, right? Just keep the duplicated one for once, right? So you got 1, 2, 3, 5. Again, 1 shouldn't appear for twice, and 3 shouldn't appear for twice because we need to deduplicate. You know, viewpoint of the events, we say when A and B are events, the union of A and B actually represents a third event. That event just says even A or even B happens, or both of them happens. Okay, the second operation is called intersection. So as the name suggested, right? Intersection just means I take the common elements out of the two sets. This is a notation of doing the intersection, right? So the intersection of two sets, A and B, is the set of all the elements in both A and B. When A and B represent events, the intersection of A and B means another event. That event represents both even A and B happen. For example, one event could be tomorrow there will be a snow, And another event, say B, could be tomorrow it will be very cold, right? And then the intersection of A and B just means a third event. Tomorrow is not only snow, but also very cold. So let's see some example, right? So going back to the examples we mentioned, right? So A represents the event you got an off row, right? And B represents events you got a row of 3 or less, right? Then the intersection of A and B, you see it's just 1 and 3, right? Why? Because 1 and 3 belong to both A and B, so just take them out, right? This actually represents the event, meaning that you have an odd row of 3 or less. Does this make sense? Okay. Sometimes if A and B doesn't contain any common elements, then their intersection is the so-called empty set. In this case, we also say A and B are disjoint. Right? We can use a graph to represent things like this, right? We can use this called Venn diagram. Maybe I'm saying this in other places, right? So I can draw one closed area to represent even A, and another area represents B, right? So the overlapping part represents the intersection between A and B. And if you mark the total areas A and B cover, it represents A union with B, right? So let me do this. You mark all the areas that are covered by both A and B. So this is called the union between A and B. It's actually a very useful graph tool to expose the relationship between the sets. Okay. A third operation we want to introduce is called complement. So suppose we have a set A, and it belongs to some larger set omega. In the probability scenario, A could be some even, and omega represents the sample space, right? Then we denote the complement of A by this A to the power of C. Okay? So A to the power of C includes all the elements in omega, but not in A. So basically, excluding all the elements in omega, excluding all the elements in A from omega, then you got the complement. So let's say example, right? So again, this event, you got an out row that represents a set 1, 3, 5, right? And what's the sample space? What's the omega? Anyone give? Yes, 1 through 6, right? Sample space includes all possible outcomes of your result, right? Of your experiment, right? So it's 1, 2, 3, 4, 5, 6, right? And then the complement of A is just excluding from omega all the elements in A, which is we're gonna exclude 1, 3, 5, right? The remaining elements form the complement of A, which is which is 2, 4, 6. That's complement of A. Okay. Right. It's here, right? So, well, A represents an event, right? So the complement of A, it actually represents an event that even A does not happen. Like, for example, an event, I might define an event like tomorrow there will be snow. Okay? The complement of my event is tomorrow there won't be a snow. Right? And tomorrow another event could be okay. Tomorrow I will get up late, right? And the complement of the event will be tomorrow I won't get up late. Okay. And next, we're going to introduce the set operation is called difference. Right? It's like the subtraction, right? But when we talk about subtraction between sets, it's not really talking about, okay, you're gonna subtract number 1, number A from number B. It's not like that, right? It's just talking about excluding common elements. Let's see the definition first, right? So the difference of a set A, which belongs to the universal set omega, and set B, which also belongs to omega, then we denote it by A minus B, right? This represents a new set which includes all elements in omega that in A but not in B. It's a little bit, long about definition, but we'll see it very clearly from the examples. So suppose this is my set A, 3, 4, 5, 6. And this is my set B, 3 and 5. A minus B just means I just look at all the elements in A, but not in B. Right? So we see that 3 in A, but also in B, right? I'm gonna exclude it. And
好的，我在网上找到了这个与老鼠硬币有。
sorry, this is a stupid Siri pop up. And 4 is in A, but not in B. So it should be included in A minus B. And 5 in A and also in B. We should exclude it. And 6 in A, but not in B. So eventually A minus B is just 4 and 6. You see that, right? So it's just looking at which elements are solely in A, not in B. That's A minus B. Subtracting here means that I'm gonna excluding the common elements between A and B and say what's the remaining elements in A. That's the idea. Any question? Everyone's comfortable? Okay, great. Yeah, perhaps I want to do another example. So A might be 1, 2, 3, 4, and B is 1, 2. So what is A minus B? I heard that, right? It's 3 and 4, right? Because A minus B just excluding the common elements in A and B from A, right? So the remaining will be just the 3 and 4. Okay, so now I want to ask, what is B minus A? Any thought? Why is empty? Exactly, right? So follow the definitions. So you see that all the elements in B are also in A, right? You're gonna exclude all of them, then there's nothing in B. So we arrive at an empty set, right? So that's why we should be careful about this set difference. It's not like A must have more numbers than B, then you can do A minus B. You can do A minus B, you can do B minus A, you can do minus B, you can arbitrary pair of sets. The requirement is that you have to exclude their common elements, right? So when we subtract B from A, you see all elements in B are also in A, so you remove all the elements in B, you see there's the empty set. Okay. Another interesting observation is that A minus B, or difference between B, can be equivalent written as the intersection between A and the complement of B. Okay. This one can be illustrated more intuitively by using the Venn graph we just showed, right? So suppose this is your A, okay, and this is your B, right? According to the definition, A minus B is actually excluding the common elements in both in the B, A and B from A, right? So the common elements is the overlapping part, which is here, right? And that means A minus B will be this part, right? This black part. Right? And we can also check what does it mean for A intersection with B complement, right? So what is B complement? How can we represent B complement in this graph? You know that, okay, suppose this is their whole set, right? So B complement are all the elements not in B, right? So that will be, let me use a different color. So that will be all the areas outside B, right? And then we intersect B complement with A, that blue circle, right? You see the intersection, the overlapping part will just be this part, right? And you see the kind of completely the same as the black lines, those parts covered by the black lines, right? So that's a simple way to show why these two are equivalent. Any questions so far? Okay, great. So I highly recommend you guys to use this Venn diagram to draw things and to get a better perception or intuitive perception about the sets and their operations. Okay, so there's a famous law about sets. It's called De Morgan's laws. Perhaps you have heard them before. So it says that if you take a union of two sets and then take the complement, it is the same as you first take the complement for A and B and then take the intersection. And you kind of like symmetrically, you exchange the union and intersection, the results still hold, right? So you take the intersection between A and B and take complement. It's the same as you take the complement and then take the union, right? So here we just we want to use the Venn diagram to show the equivalence just for this, right? And for the second one, I will leave you as an exercise to play with this Venn diagram. Right? So let's see how we can graphically show this is correct, right? So you got a set A, right? You got a set B. Okay. If we first do the union of A and B, right? So of course we're gonna have assume that there's a universal set omega, right? If you first do the union of A and B, right, it will be just here the overall area which is covered by both A and B, right? Then you do the complement, you know, that means the outside region, right? That will be this place, right? Any other places which is outside of their region, the jointly covered, right? Okay, so all those red places are the complement of A union B. Right? Does everyone agree? Okay, so let's see. How about the right hand side, right? So yeah, maybe I should draw another graph. Otherwise, it's really messy. So you got A here, B here, right? So if we look at the complement of A, right? So we see that it will be all area outside of A, right? Basically, you can view those black lines covered region. They are all just outside of A, right? Now, if you look at the complement of B, right? So that will be all the outside region of B, right? So look at this. It's just the region covered by the green lines, right? And then you take the intersection. You take the intersection, you want to look at all the areas you both have black and green lines, right? So that means it will be the area of here, all the area outside of here. You have those mixed green and black lines. Right? You see, actually, they are representing the same thing, right? Any questions so far? Yeah, again, we encourage everyone to draw this graph to show this equivalence, right? And similarly for the second law. Right? Okay. So here we give additional exercises for everyone to check, right? How does different operations when we combine them can be equal to others, right? So it is easier to use the Venn diagrams to show this, right? For example, the difference between A and B must be a subset of A, right? You can see that directly from the definition, but definition is too long, right? So, but if you draw a graph, that will be much more intuitive, right? This is A, and this is B, right? And A minus B is taking all the elements in A, which do not belong to B, which is are just these places, right? So of course, these places are just a subset of this blue circle A. So that's why we sure we see that A minus B will be a subset of A. And you can use similar way, like using one diagram to show all those results, which we're gonna skip it and leave it as an exercise for everyone. Okay, so now here it comes to the definition of probability, right? So you see that we first introduce sets, right? And the property of sets and the operations of sets, and then we introduce the concept of a sample space, which kind of like include all possible outcomes for your random experiment. And based on sample space, you can define a lot of events, right? Events are just a subset of sample space. Then comes to how do we quantify the chance of a particular event to happen, right? That's why we introduced the concept called probability, right? So what is probability? A probability essentially is a function, right? So it is defined a finite. Here we just talk about finite. I want to mention that actually probability function in general can be defined on infinite set. But here let's just talk about finite sample space omega. For a finite sample space omega, a probability function will assign every event A in this sample space a number between 0 and 1. This number characterizes the chance the event A occurs. That's called probability. So see that the probability essentially is just a function which maps from a big set, which is called sample space, to a number, right? To a number between 0 and 1. Right? And for every event which is belongs to the sample space, you're gonna evaluate the probability function over A. You give the chance that event happens, right? But we have some like a restriction about probability, right? So it's not like you can assign arbitrarily such functions. You have to make sure that the probability of the sample space is 1. That is natural, right? So omega represents all possible outcomes, right? That means like you run some random experiments, your outcome could be every possible outcome. Then this event happen, the chance must be 1, right? Because there won't be any event there won't be any event whose results is out of the sample space. That's why this probability must be the probability over the sample space must be 1. Right? I mean, to be more concrete, like say, suppose your experiment is to roll a die, right? Your sample space is just 1 through 6, right? Then the probability over omega just means what's the chance that you roll a die and you got point to be 1 or 2 or 3 or 4 or 5 or 6. The chance must be 1, right? Because it must be either of any of this point inside this range, right? It won't be 7, it won't be -1, it won't be 0. So that's why we require that your probability function over the sample space to be 1. A second thing is also very important. When you have 2 events, A and B, and the intersection of the 2 events is empty, then the probability over the union of A and B, remember, this represents another event, is written as the probability of A plus the probability of B. Okay. So basically means that if A union with B is empty, then the probability of A union with B, this means that the probability of A happens or B happens, is the summation of the probability for every event happens. Okay. But this only is valid when the intersection of A and B is empty. If it's not empty, you don't have such kind of conclusion. So this is the definition of probability. So it's essentially a function. The function map the event to a number between 0 to 1. It's a formal definition. Okay. So now let us look at some like a very simple probability calculation, right, which we call equal likely outcomes. So first we introduce the notation. If we put these two it's like a bracket that's not bracket, it's just a vertical bars, right? Over A, over set A, it just means the how many elements are in A. Like, for example, if A is 1, 2, 3, then the two vertical bars inside A, outside A, it just means 3. Right? It just denotes the size of the set. So we're going to construct a probability function that every element, every outcome of your experiment has the same chance. So like you roll a die, right? If it is a completely random, right? And the material is also kind of very proper, very ideal, then you know that you have equal chance to get 0.1, 2, 3 through 6, right? So in that case, we have equal likely outcomes, right? Then for any event of your rolling die experiment, right, which is a subset of those points, right, the probability for that event is just the size of A divided by the size of the whole sample space. And let's see some example, right? Rolling a 6-sided die. Right? So we know this every outcome has the same chance, right? So that basically means the probability you see 0.1 is 1 over 6. And of course, probability you see 2 is 1 over 6 as well, and so on. And then what is the probability of you say 1 or 2 or 3? As we mentioned, it's just the size of your event over the size of the sample space, which is 3 over 6, 1/2. Right? Does it make sense? Okay. Next, we'll come to the so-called repeated experiments, right? We mentioned that a moment ago, right? Suppose we also perform for twice, right? How do we construct the sample space, right? If we do 2 rounds of an experiment with the same sample space omega, it's just like you roll a die for twice, right? And we know that you have like 2 outcomes, right? From these 2 experiments. You're going to combine them together as your result. So then your sample space is written in this way. It's like omega multiplied with omega, and this is not number multiplication, right? It just means like, how do we combinatorial enumerate pairs of elements in the first omega and in the second omega. So if we write it in this way, right, it will be just x pairs, xy pairs, and where x belongs to omega and y also belongs to omega. Right? So this pair is called an ordered pair. And in this scenario, the order is very important because it represents what is the first experiment's outcome, what's the second experiment outcome. If you switch the order, that means you have different results, right? For example, suppose you roll a die. You toss a coin for twice, right? So your one outcome, one result of your rolling, your tossing experiment could be H and T. It just means in your first for tossing, you see heads up, and second for tossing, you see tails up, right? It's different from that another pair, T and H. Why it's different? Because this represents your outcome of the first tossing is tail, and the second is head. And then if you look at the whole sample space, right, which we have written down before, right? Just rewrite it. So you see that it contains H, T represents your first tossing head and second tail, and T, H, first tail, second head, H, both tossing gives heads up, and T and T, right? That's your sample space. You see that it actually corresponds to our more general notation, right? You just enumerate all pairs, where each pair, inside each pair, the first element comes from the first sample space, the second element comes from the second sample space. Any questions so far? Okay, great. So, yeah, this one was covered, right? All the matters and repeats are also possible. It's like H just represent you have the first outcome. You have the outcome as H for the first tossing, and the second outcome to be the same result of the second outcome, right? So we can extend it to n times, right? Suppose we repeat one experiment for n times, and then you have to extend your sample space as well, because you have to record every outcome of your every experiment, of each of your n experiments, right? So you're gonna have this n elements together form one result of your experiments, right? And this set, we can write it as omega times omega. I omega to the power of n. Again, this is not talking about you doing some power or multiplication over numbers. It just represents the sets, right? And this element, which includes n outcomes from the n experiments, is called an n tuple. Again, this is just a notation. So it's natural to see that if your sample space for one experiment contains k possible outcomes, right? If you repeat this experiment for n times, how many possible results? For one experiment, you have possible k outcomes, right? And for another experiment, you also have k possible outcomes, right? So their combination will be k times k, right? Right? If you have a third experiment, you still have k possible outcomes. If you combine with the results from the first two experiments, you have in total k times k times k outcomes, right? And in general, if you do the experiments for n times, then your total outcomes will have k to the power of n, right? Which is just the number of all those n tuples. Any questions so far? Okay, great. So let's stop here today and see you on next Tuesday. Don't forget to take the quiz.